Management, Chapter 14, Part 2, Design Principles for a Rainwater Harvesting Structure. When I first considered the idea of designing a water harvesting structure for our neighborhood, I didn't know it would become such a detailed and community-driven work. My goal was to develop a location-specific solution, one that would not only serve immediate water needs but also strengthen our collective capacity to manage resources sustainably. The first step was to conduct a thorough preliminary survey. I gathered administrative details, assessed the available roof area, and documented surface characteristics. I had to understand the local geology and geomorphology and check for any existing water quality issues. The portable water demand in the area guided the overall planning. My mobile app helped me log coordinates, water yield, and even geomorphological zones based on Bhuvan maps and hydrogeomorphological references. Once I understood the lay of the land, I moved on to design and estimate. I maximized water utility by reviewing old borewell reports and water testing data. I prepared a material inventory and referred to the government schedule of rates. A key realization was that different buildings required different tank sizes. I calculated the recharge capacity as the product of the total roof surface area, the average rainfall of our locality, and the runoff coefficient based on the roof material. A simple formula helped me estimate the tank volume at 20% of the roof area. The height of the tank had to be no less than 9 feet, so I adjusted dimensions accordingly. Then came construction. We selected a site upstream from an existing well to help assess recharge impact. Earth cutting began using both manual and mechanical efforts. We filled the pit's base about 4 feet deep with altering layers of sand, gravel, and boulders for natural filtration. To prevent collapse, we built brick walls along the pit's 5-foot depth. The plumbing layout connected rooftops via pipes to the tank. We installed a valve right before the borewell junction so we could flush out the first rain's debris. In case where the site has limited space, we used borewells with slotted casings at the aquifer's depth to allow sideways percolation. Before handing over the structure to the community, I supervised a trial run. We filled the system using RO water during the first rain just to check the functioning. At every stage, I kept track of timelines, resource allocation, and even the labor involved because successful water project depends as much on management as on design. Operation and maintenance was integral to our plan. We engaged a local caretaker and developed protocols for operation and management. The first flush was crucial. We taught the caretaker to measure the flow rate using a sensor, routinely inspect for leakages, and ensure that the water did not overflow. The community was trained to look for blockages and supported in cleaning and recycling efforts. We even tried adding a transparent ceramic cover to improve aesthetics. Technology offers new possibilities. We now may try a borehole camera to understand the subsurface movement. This may be linked to an IoT-enabled dashboard to get real-time data. In the near future, we may plan to connect them with conservation-promoting apps so that households can track their contributions to water saving. The entire process from survey and design to construction, community engagement, and innovation taught me that water harvesting is a social commitment grounded in science, sustained by local action and driven by trust. Thank you.